fascinating material today, an analysis that takes on a pretty mind-bending challenge.
Yeah.
Comparing and contrasting particles, planets, and stars.
It almost sounds absurd when you first hear it, doesn't it? You've got something practically non-existent in scale, then a whole world, and then these giant cosmic powerhouses.
Right, exactly. And yet, this deep dive into the sources, it reveals some incredibly surprising connections and also some really defining differences that tell us, a lot about how the universe is actually put together. Think of this as your shortcut, sort of, to understanding the fundamental architecture of the cosmos, from the tiniest bits right up to the grandest structures.
So how can things that are so dramatically different share anything meaningful?
That is the million-dollar question, isn't it?
Okay.
Okay, let's unpack this. First step, probably best to set the stage with some definitions, based on our material. What do we actually mean by each of these cosmic constituents?
Okay, so when this analysis talks about particles, it's focusing primarily on the fundamental building blocks. We're taking the subatomic realm here.
Okay.
That means elementary particles, things like quarks, leptons, electrons, neutrinos fall into that category. And also the composite particles they form, like protons and neutrons, the stuff that makes up the nucleus of atoms.
Got it. So the really basic ingredients. Then we scale up quite a bit to planets.
Right, planets. As defined here, they're large celestial bodies. They orbit a star. The key criteria are they need to be massive enough for their own gravity to pull them into a roughly spherical shape.
Okay.
They've cleared their orbital path, swept up the major debris. And crucially, they do not generate energy through nuclear fusion in their core.
No fusion. That's the key differentiator from stars there.
Exactly. And they can be rocky, like Earth or Mars, or they can be gas giants like Jupiter or Saturn.
Our home turf and its neighbors. Okay. And finally, the real giants, stars.
Stars, yeah. These are immense luminous spheres of plasma, all held together by their own gravity. Their defining characteristic, and this is what separates them so sharply from planets, is that they do power themselves through nuclear fusion in their core.
Ah, the fusion engine.
Precisely, converting hydrogen into helium, mostly, and releasing just vast amounts of energy. They're the engines of their solar systems.
Okay. Definitions locked in. Now, this is where the really fascinating insights from our source material start popping out. You'd think, you focus on the massive differences, right? But the analysis, it actually reveals these fundamental similarities that are, well, frankly, quite striking given the scales involved.
It's quite remarkable, really. Despite that huge gulf in size and complexity, they are all fundamentally built from the exact same stuff.
Yeah.
Planets and stars are composed of atoms, and atoms at their core are just arrangements of those very same subatomic particles we just talked about.
The quarks and leptons?
Quarks and leptons. It's like the same cosmic Lego set, just put together in wildly different ways.
That's a great analogy. And because they share that foundation, it means they all have to play by the same rules, the universal physical laws.
Exactly. Take gravity, for instance. It's obviously the dominant force for planets and stars, right?
Yeah.
It governs their formation, their structure, how they move through space-time.
Sure.
But the analysis reminds us, even particles, because they possess mass energy. Well, they are also subject to gravity. It's just that the effect is vanishingly small at their individual scale compared to the other forces acting on them.
Almost negligible, but it's there.
Okay.
Then you've got electromagnetism.
Oh, absolutely essential. It's what binds electrons to atomic nuclei, making up the matter in planets and stars. It dictates how plasma behaves in stars, influences planetary magnetic fields.
And it's how starlight reaches us, right?
Exactly. It's fundamental to how stars emit light. And then there are the nuclear forces.
The strong and the weak.
Right. The strong force is like the cosmic glue holding quarks together inside protons and neutrons. And it binds the atomic nuclei themselves. That's fundamental to the stability of all matter in planets. And it's the basis of fusion in stars.
And the weak force. Where does that come in?
Well, the weak force is involved in processes like radioactive decay that provides some internal heat for planets, And it's also crucial for certain types of fusion reactions in stars.
So these four fundamental forces, they're knitting everything together. Just their influence, their dominance changes dramatically depending on whether you're looking at a particle, a planet, or a star.
Precisely. The scale and conditions dictate which force rules.
And another shared thing. They all possess mass and energy, bound by that famous equation EMCT sub.
Yep. A particle has its intrinsic mass, and the immense mass of planets and stars is just the collective sum of all their constituent particles' mass and energy.
And they all exist within within space-time.
Yeah.
the four-dimensional fabric of the universe.
And their presence, especially the really massive objects like stars, actually warps that fabric. That's what we perceive as gravity.
Which brings us to another connection mentioned in the material. They're all part of larger systems.
It's systems within systems, isn't it? Particles form atoms, atoms form molecules, molecules build planets.
And planets orbit stars and solar systems.
And stars live in galaxies, which are part of galaxy clusters, which form superclusters. It's structure built upon structure, scale upon scale.
Yeah, it really drives home that nothing in the universe truly exists in isolation.
Absolutely not.
Okay, so that's the common ground. Shared building blocks, shared laws, being part of bigger structures, that lays the foundation. But let's be real, what makes them distinct? The differences are just staggering. That's where the unique nature of each really shines through.
Oh, completely. The most obvious one has to be scale. The sheer difference in size is almost. You can't really wrap your head around it. Proton is something like, what, 10 to the minus 15 meters across?
Inari?
Earth is roughly 10 to the 7 meters. So that's, let me think, 22 orders of magnitude difference just in diameter.
22 zeros, wow. And the sun compared to a proton.
The sun's about 10 to the 9 meters, so now you're talking 24 orders of magnitude difference between a fundamental particle and a star.
Okay, that's just,
Yeah.
mind-boggling.
And the mass difference is equally vast, from a tiny, tiny fraction of a kilogram for a particle up to maybe 10 to the 32 kilograms for a really massive star. This difference in scale, it's probably the single most defining characteristic separating them.
And that scale difference, it must directly impact what they're made of, right? I mean, how they're put together.
Absolutely. Even though they start from the same fundamental particles, how they're assembled differs hugely. Particles are either fundamental themselves or simple composites, like 3 quarks and a proton.
Pretty basic structure.
Yeah. Planets, on the other hand, are incredibly complex chemical mixtures. You've got silicates, metals, volatile ices, different gases, sometimes complex organic molecules.
A real grab bag of elements.
Whereas stars, in bulk, are remarkably simple. They are overwhelmingly hydrogen and helium, just in a super high-energy plasma state, with only tiny trace amounts of heavier elements mixed in.
Okay, composition is starkly different. What about energy? That seems like a big one.
Oh, it's a key distinction the analysis really emphasizes: their energy source. Particles have intrinsic energy, like kinetic energy if they're moving, but they don't generate energy internally, they just are.
Right, and planets.
Planets mostly get their energy from their parent star. Absorbed sunlight is the big one. Plus, maybe some leftover internal heat from when they formed, or heat from radioactive decay inside, or tidal forces if they're orbiting close. But they're passive recipients, basically. Or they exploit existing energy sources.
They're not making their own heat and light, fundamentally.
Exactly. Stars, however, are active generators. They create truly immense amounts of energy through nuclear fusion happening right down in their cores. That is the fundamental process that defines a star.
And that leads directly to luminosity, right? How bright they are.
Directly. Particles don't emit visible light just sitting there. Planets, well, they shine by reflecting the light from their star.
Like the moon or Venus in the night sky.
Precisely. Stars, though, are self-luminous. That fusion energy works its way to the surface and gets radiated out across the entire electromagnetic spectrum. That's why they shine.
Makes sense. And we talked about the fundamental forces applying to all three, but you mentioned their dominance changes.
Yeah, that's another key difference. For individual particles, it's really the nuclear forces, strong and weak, and electromagnetism that are paramount. Gravity's effect is essentially zero at that level.
Okay, but scale up to a planet.
And gravity becomes king. It holds the planet together. It dictates its orbit around the star. Electromagnetism is still important, of course, for its structure, its magnetic field, interactions.
And for stars, it sounds like a battleground.
It really is. You've got gravity relentlessly trying to crush the star inwards. But fighting against that is the immense outward pressure generated by the nuclear fusion in the core. So for stars, gravity, the nuclear forces, and electromagnetism are all playing these crucial dominant roles in a dynamic balance.
Fascinating. What about inside? Their internal structure must be different too.
Completely. Particles are fundamental, or they have a simple substructure, like the quarks and gluons inside a proton. Planets, though, they differentiate. They form layers based on density and composition.
Like Earth's core, mantle, and crust.
Exactly, or the gaseous envelopes and metallic hydrogen cores you might find in gas giants. Stars also have layers, but they're driven by how energy moves outwards. You get a fusion core, then maybe a radiative zone where energy travels as photons, a convective zone where hot plasma rises and cool plasma sinks, and then the star's atmosphere.
Different layering principles. Yeah. Okay, temperature. Must be huge differences there.
Oh, immense. We talk about the kinetic energy of particles, but for collections, we can talk temperature. Planet surfaces have wildly varying temperatures depending on distance from the star, atmosphere, etc. But their interiors typically get up to thousands of Kelvin.
Hot, but not star hot.
Not even close. Star surfaces are also in the thousands of Kelvin, similar to maybe a planetary core, but their cores, that's where fusion happens. You need millions, sometimes even billions of Kelvin for that.
Right, that fusion threshold. Okay, and how long do they last, their life cycles?
Totally different timescales and processes. Particles can be created in high-energy collisions. They can be annihilated if they meet their antiparticle, or some can decay into other particles.
Relatively quick events, some of them.
Sometimes, yeah. Planets, they form alongside their stars and then evolve geologically, atmospherically over billions of years. Their ultimate fate, though, is often tied to their star. They might get engulfed when the star expands or just drift off if the star dies gently.
So billions of years of relative stability, then potentially oblivion.
Pretty much. Stars, though, they have these really dynamic lives, and it all depends heavily on their initial mass. They form from collapsing gas clouds, then most spend a long time in a stable fusion phase, the main sequence.
Like our sun currently.
Exactly. Then they evolve, often puffing up into red giants, and their end state depends on mass. Lower mass stars, like the sun, end as white dwarfs, while massive stars can end in spectacular supernova explosions, leaving behind neutron stars or even black holes.
Much more dramatic endpoints for the big ones.
Definitely. And that ties into their fundamental role in the universe, which also differs hugely.
How so?
Particles are the absolute foundational ingredients, the bricks. Planets are complex assemblies built from those blocks, and crucially, they're the places that might be potential environments for life.
They're potentially habitable real estate.
Right. And stars. The analysis positions them as the universe's crucibles and its power sources. They're the ones that create the heavier elements needed for planets and life in the first place. They provide the energy that sustains planetary systems, and their collective gravity and energy output drives the evolution of entire galaxies.
So particles are the bits, planets are the places, stars are the engines and factories.
That's a good way to put it. The analysis also touches on density variations. Atomic nuclei themselves are incredibly dense.
Way denser than everyday matter.
Oh, yeah. And you have planets like Earth, around 5.5 grams per cubic centimeter on average. But a gas giant like Saturn is actually less dense than water, less than 1 GCMO.
Famously, it would float in a giant bathtub.
If you could build one. And the sun averages about 1.4 GC-meter, but its core is vastly, vastly denser than its outer layers. Density varies a lot.
Okay. And one last difference mentioned. The physics that governs them. Quantum versus classical.
Yeah, that's important. Particles are squarely in the realm of quantum mechanics. Their behavior just doesn't make sense without it. Planets, on the macroscopic level, the big picture, are largely described by classical physics, Newtonian gravity, thermodynamics, although quantum mechanics is still essential for understanding their atomic composition and chemistry.
Sure, the materials they're made of rely on quantum rules.
Right, and stars are similar. On a large scale, gravity and fluid dynamics, largely classical. But their core processes, nuclear fusion, how plasma behaves under extreme conditions, absolutely rely on quantum mechanics. You can't explain a star without it.
So it's a mix, but the dominant description shifts with scale.
Exactly.
Okay, so to pull that thread, they start with the same basic ingredients, play by the same fundamental rules, but the vast differences in scale, in energy generation, and in which forces dominate lead to these completely distinct kinds of cosmic objects.
But crucially, they aren't just separate categories sitting there independently. The analysis really stresses how they're linked. It's a continuous, dynamic, cosmic dance.
Right. It's not like they just appeared separately. There's a direct lineage, isn't there, from particles to stars and planets?
Absolutely. The universe kicked off as this hot soup of fundamental particles right after the Big Bang. As things cooled down, these particles combined to form the simplest atoms, mostly hydrogen and helium.
The primordial elements.
Then gravity took over, pulling these simple atoms together into enormous clouds, what we call nebulae. These nebulae then collapsed under their own weight.
And ignited.
Forming the very first stars.
Okay, so stars came first from the initial gas. Where did planets come from?
From the leftovers. The material swirling around those early stars, which, importantly, had already been enriched with heavier elements forged inside previous generations of stars that had lived fast and died young. That leftover disk of gas and dust clumped together. Gravity pulled it into planetesimals, then protoplanets, and eventually full-blown planets.
So the particles from the very beginning are literally the ancestors of the atoms in planets and later stars today.
It's a direct line, and it's a cycle. Which brings us back to the star's role as these cosmic forges.
Stellar nucleosynthesis, creating new elements.
Precisely. Fusion in the cores of stars doesn't just provide energy. It actively creates heavier elements, working its way up the periodic table, mostly up to iron for typical fusion.
But we have elements heavier than iron. Where do they come from?
That's where the massive stars come in. When they run out of fuel and collapse, they explode in supernovae. The analysis points out that these incredibly energetic explosions provide the conditions needed to forge elements even heavier than iron.
Gold, silver, uranium.
All that stuff, and the supernova doesn't just make them, it blasts them out into space, scattering them through the galaxy.
Seeding the next generation.
Exactly. That scattered material becomes the raw ingredients for the next round of star formation, and the formation of new planets, now richer in these heavy elements. It's the universe's ultimate recycling program.
Wow. And the analysis makes the point that this whole cycle, right down to the energy coming out of stars, the radioactive heat inside planets, and it's all fundamentally underpinned by particle physics, isn't it?
Absolutely. Nuclear fusion is particle physics. It's about how atomic nuclei interact under extreme conditions. Even something like a planet's internal heat from radioactive decay, that's a direct consequence of the properties of specific isotopes, specific atomic nuclei, how likely they are to decay, governed by the weak nuclear force.
They really are inextricably linked, not just by sharing laws, but by this shared history and this ongoing process of transformation.
You can't truly understand one without understanding the others and how they connect.
So let's try and recap this deep dive then. We've journeyed from the incredibly small to the astonishingly large. We've seen that particles are, like you said, the fundamental bricks, the cosmic ingredients. Planets are these complex, organized structures built from those ingredients. They're the potential abodes for further complexity, maybe even life.
The cosmic real estate.
Yeah, and stars are the colossal engines of the universe. They power entire systems. They drive the evolution of galaxies. And critically, they are the factories forging the heavier elements needed for planets and, well, us.
And despite those immense differences we talked about, scale, energy, the forces in charge, they're profoundly interconnected through the fundamental laws of physics and through this grand, universe-spanning cycle of matter and energy.
Understanding each piece, the particle, the planet, the star, and especially how they relate, how they transform one into the other, that seems essential for grasping the whole cosmic picture.
It really changes how you look at things, doesn't it?
It does. And here's a final thought for you, listening right now. Think about the atoms that make up your own body, the carbon in your cells, the oxygen you're breathing in this very moment, the iron carrying that oxygen in your blood. Where did those specific atoms come from? This analysis makes it crystal clear. They weren't forged in the Big Bang. Not the heavy ones, anyway. They were created painstakingly inside stars.
Yeah.
Some maybe in the relatively calm, steady fusion core of a sun-like star over billions of years. Others might have been born in the unimaginable violence of a supernova explosion billions of years ago.
We really are star stuff.
In a very real, very physical sense, you are made of stardust, forged in the hearts of stars and scattered across the cosmos. And that links you directly and intimately to the life and death cycles of these immense cosmic engines we've just been exploring.